When you see a reaction like this one, you rightly expect that it will continue until one of the reactants runs out. So if I burn the match in the open air, it will continue to burn until all the carbon and hydrogen in the wood have been converted to carbon dioxide and water. And in these cases, we commonly show the reaction with an arrow to connote that the reaction goes to completion. But most real chemical reactions don't go to completion. Instead, they proceed toward a state we call equilibrium.
Yay!
You may have run into the term equilibrium before in relation to phase changes. For example, a volatile liquid in a closed container will evaporate until the so-called vapor pressure of the liquid is reached. Remember that this is a dynamic equilibrium. That is, even though the total number of molecules in the gas phase doesn't change over time, molecules continue to transfer back and forth between the gas and liquid phases. Consider a closed bottle containing the gas NO2, which it turns out is orange in color. We'll show you what the gas looks like in the first picture and the chemical composition in the other. Now NO2 undergoes the following reaction. We say it dimerizes to form the colorless gas N2O4. So let's start the reaction. Notice that some of the NO2 molecules dimerize, but gradually as more and more N2O4 molecules accumulate, some of these spontaneously split back up to form NO2. At a certain point in time, the rate at which NO2 molecules are dimerized equals the rate at which N2O4 molecules are splitting up. At this point we say equilibrium is achieved. Notice the reaction has not gone to completion, but instead to equilibrium. And for this reason we often use forward and backward arrows, or to save trouble, an equal sign, rather than a forward arrow in writing the reaction. Again, this equilibrium is dynamic. Even though the total amount of NO2 in the container is staying the same, the conversion back and forth between NO2 and N2O4 continues. One of the nice things about chemical equilibrium is that it's well defined and reproducible. For example, if I put some NO2 in a container, the reaction to produce N2O4 will always stop once the relative amounts of NO2 and N2O4 have reached the same values. Now, what do I mean by this exactly? In other words, what characterizes the equilibrium state? Well, for gases, it is the gas pressures of NO2 and N2O4. And when we combine these in just the right way, the equilibrium state is defined for all circumstances. It turns out that the combination that works is this. In other words, every time I mix any amount of NO2 and N2O4 in a container, the reaction will proceed until the ratio you see here reaches the same value. Then it will stop. Isn't that amazing?
Wow!
And what's even more amazing is that it works in either direction, whether we start with NO2 and react to produce N2O4, or we start with N2O4 and react to produce NO2. So what is this magic ratio? Well, at room temperature, it's approximately 3. And where did this ratio come from? Well, that's the most amazing part of all, because for any reaction, this ratio can be easily derived from the balanced reaction. Watch. Here's the balanced reaction. We take the pressure of the product, in this case N2O4, raised to the power of its coefficient in the reaction, in this case 1. That is the numerator of the ratio. Now we take the pressure of the reactant, in this case NO2, raised to the power of its coefficient, in this case 2, and use it as a denominator. And that's the ratio that defines the equilibrium. Now we can do this with any reaction involving gases, and by golly it works. So we give this ratio a name, the equilibrium constant for the reaction. Every reaction has its own unique equilibrium constant. Gas reactions aren't the only ones that have equilibrium constants. Let's look at an example of equilibrium in solution. A weak acid will serve our purpose. Let's look at some of the acetic acid that I used earlier on my fish and chips. As you probably know, acetic acid dissociates in water this way. Now, because the acid is weak, the reaction doesn't go to completion, but to equilibrium. And how do we define the equilibrium? Well, we obviously can't use pressures. Instead, for solutes in solution, we use molar concentrations. So the equilibrium is defined as, using the ratio of products over reactants, we multiply the concentration of all products raised to their respective coefficients, then divide by all reactants. In this case, just the concentration of acetic acid raised to its coefficient. And lo and behold, this indeed is the ratio of concentrations of these species in solution once equilibrium is achieved. So let's take a look at what happens to the acetic acid when we put it in water. At first, the acetic acid molecules begin to ionize into hydrogen atoms and acetate ions. But as the concentration of ions increases, some of these begin to recombine to form acetic acid molecules again. At a certain point, the rate at which the forward and reverse reactions occur balances out, and equilibrium is achieved. Let's look at some typical values of equilibrium constants and see if we can make sense of what they mean. For example, here's that same reaction we just saw for the ionization of acetic acid in water. And here's the expression for the equilibrium constant. And by the way, these constants are typically represented by the capital letter K. The value of this constant at room temperature is 1.8 times 10 to the minus 5. So what does this imply? Well, this is a very small number, isn't it? So, at equilibrium, which is present in greater abundance, acetate ions or acetic acid molecules? Another way of asking this question is, in a solution of acetic acid, which form of acetic acid species is predominant? Pick the button you think is correct.
Yay!
Since acetate ion is in the numerator, and the ratio is a very small number, the species present in greatest number at equilibrium must be unionized acetic acid molecules.